Area of a surface of revolution. When a function y equals f of x is revolved around the x-axis, we get a three-dimensional shape. And for this three-dimensional shape, we can find the volume by using the method of disks and washers or the method of cylindrical shells. But this three-dimensional shape also has a surface area, particularly a lateral surface area, and that is the area of the material that would be formed around the sides of this figure once it's revolved around the x-axis. And just to be clear, we are not looking at the area of the end here or the area of the end here. We are only looking at the lateral surface area. So how do we find this? Well, of course, what we do is we take our interval from A to B and we divide it up into subintervals. And when we do that, we can approximate the lateral surface area of this band by using some geometry to come up with a formula for the surface area of this shape. And the formula for that is 2 pi times f of xi star times the square root of 1 plus f prime of xi star squared times delta x. Now you'll notice that it's related to the length of the arc, and that is because the length of the arc is the lateral height of this figure. And so I'm not going to get into the precise derivation of this formula, but what we need to do is add up all of these approximations and then take the limit as n goes to infinity. And when we do that, we get the following formula. So the surface area S is equal to the limit as n goes to infinity of the sum from I equals 1 to n of essentially this. And we know that when we do this, this is a Riemann sum, and a Riemann sum can be transformed into a definite integral. So this is the formula for finding the surface area when revolving the function f of x about the x-axis. So here is that first formula here. Now, when revolving a function about the x-axis, you can also do it with respect to y. So we have an alternative formula here. Now, please understand this is for functions revolving about the x-axis. So you can do it with respect to x, or you can do it with respect to y. Now, if you do it with respect to y, the limits of integration have to run along the y-axis. When you do it with respect to x, the limits of integration have to run along the x-axis. And then you can also revolve about the y-axis. And if you revolve about the y-axis, you can do that with respect to y or with respect to x. And again, when doing it with respect to y, you use limits on the y-axis. And when doing it with respect to x, you use limits on the x-axis. Let's do some examples. So here we have the curve y equals the square root of 4 minus x squared. And it's basically just an arc of the circle x squared plus y squared equals 4. We want to find the area of the surface obtained by rotating this arc about the x-axis. And just to be clear, we're only rotating from x equals negative 1 to x equals positive 1. So since we're going about the x-axis, we know the surface area will be 2 pi times the integral from a to b of your function f of x times the square root of 1 plus f prime of x squared dx. Now for us, our function f of x is the square root of 4 minus x squared. We need to know our derivative. So let's think of our original function as 4 minus x squared to the 1/2 power. The derivative will be 1/2 times 4 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. And if we simplify this, we get negative x over 4 minus x squared to the 1/2. Notice that the 2's cancel out here. And this can be written as negative x over the square root of 4 minus x squared. So when we plug this into the formula above, we get the surface area is 2 pi integral from x equals -1 to x equals +1 of our function, which is the square root of 4 minus x squared, multiplied by the square root of 1 plus the derivative quantity squared. And then now we just need to simplify and integrate. So let's go ahead and work on the inside of the radical. I'm going to do that separately here. So what we have there is 1 plus, and then negative x quantity squared is the same as x squared. And then when you square the radical here, you just get the inside, which is 4 minus x squared. So we can write this as 4 minus x squared over 4 minus x squared. That's how we represent 1, plus x squared over 4 minus x squared. And when you add these together, you get 4 over 4 minus x squared. And so what we have here is the surface area is 2 pi integral from -1 to 1, square root of 4 minus x squared, times the square root of 4 over 4 minus x squared. Now, if you go ahead and take the square root of the top and the bottom here, the square root of 4 is going to be 2. And then you have square root of 4 minus x squared, and then times 1 over the square root of 4 minus x squared. And so notice that these completely cancel out. So this integral actually works out to be very easy. It is just 4 pi integral from -1 to +1 of dx. And this is 4 pi times the antiderivative of 1 is just x. And this goes from -1 to +1. So this is 4 pi times 1 minus -1. And this, of course, is equal to 8 pi. In our second example, we have a curve x equals 2/3 times y to the 3/2 between y equals 0 and y equals 3. And it's rotated about the x-axis. Okay, so notice that they've given us everything in terms of y, but we are rotating about the x-axis. So for this, we need to use the alternative formula for surface area. So specifically, I am talking about this formula right here. This is the formula you use when you're rotating about the x-axis, but you want to do it with respect to y. Now, one thing to note here is when you use this formula, y is just y. You don't actually have to plug in the function. It is simply the variable y. All right, let's go back to the problem. So for our problem, g of y is 2/3 times y to the 3/2 power. We need g prime of y. G prime of y is going to be 2/3 times 3/2 y to the 1/2. And if you simplify this, you just get y to the 1/2, or square root of y. So the formula, surface area, is 2 pi integral from c to d of the variable y times the square root of 1 plus g prime of y, quantity squared, dy. So we now know g prime of y is square root of y, so we'll plug this in. When we do that, we're going to have 2 pi integral from c to d is going to be from y equals 0 to y equals 3. We have the variable y, square root 1 plus the square root of y, quantity squared, dy. And this is equal to 2 pi integral from 0 to 3, y times the square root of 1 plus y, dy. Okay, so now how do we integrate this? We have to tap into our integration skills here. This is a simple u substitution problem. We're going to let u equal 1 plus y, du will equal dy, and if we solve for y, y will be u minus 1. Now when we make the substitution, we're going to have 2 pi integral of y, which is going to be u minus 1, and then the square root of 1 plus y will just be the square root of u, and then dy equals du. Also, when y is 0, the lower limit here, u is going to be 1 plus 0, which is 1, And when y equals 3, u is going to be 1 plus 3, which is equal to 4. So our new limits of integration are from 1 to 4. From here, we're going to multiply out the integrand. So radical u times u is going to be u to the 3 halves minus 1 times radical u is radical u, which I'm going to write as u to the 1 half. Let's go ahead and do the integration. We have 2 pi. Integral of u to the 3 halves is u to the 3 halves plus 1, which is 5 halves, divided by 5 halves, minus the integral of u to the 1 half is u to the 3 halves, divided by 3 halves. Let's go ahead and simplify just a little bit more here. We're going to say 2/5 u to the 5 halves minus 2/3 u to the 3 halves. And now we're going to plug in our limits from 1 to 4. Plugging in, we got 2 pi multiplied by the quantity. When you plug 4 in here, we're going to have 2/5 times 4 to the 5 halves minus 2/3 times 4 to the 3 halves minus the quantity. When you plug in 1, you're going to get 2/5 minus 2/3. Remember that 1 raised to any power is just 1. So next we need to figure out what is 4 to the 5 halves. So let's work on that. 4 to the 5 halves power is the square root of 4 to the 5th, which is 2 to the 5th, or 32. And 4 to the 3 halves is the square root of 4 quantity cubed, which is 2 cubed, which is 8. So plugging everything in here, we have 2 pi multiplied by 2/5 times 32 minus 2/3 times 8 minus the quantity 2/5 minus 2/3. Now we just need to finish this by doing the arithmetic. Let's bring it up above here. So what we have here is 2 pi times 64 over 5 minus 16 over 3 minus 2/5 and then plus 2/3. You need to be sure that you distribute the negative here. It would be a shame to get a problem wrong because you forgot to distribute a negative. Okay, so let's keep going. We have 2 pi multiplied by 64 over 5. Take away 2 over 5 is 62 over 5. And negative 16 over 3 plus 2 over 3 is negative 14 over 3. And then finally, we just need to combine these by getting a common denominator. So we're going to multiply the top and bottom here by 3 and the top and bottom here by 5. And doing so gives us 2 pi times 186 over 15 minus 70 over 15. Which is 2 pi times 116 over 15. And if we multiply 2 times 116, we get 232 pi over 15. Now, I want you to realize that much of this problem is very basic in nature, right? We're just doing a bunch of arithmetic here. And then back here, we're just doing standard integration techniques, a little substitution. So it's no one particular part of this problem that makes it difficult. It's just that it's a very long and tedious process. So you need to really work on trying to do lots of steps without making any little mistakes. In our final example, we want to revolve y equals x squared from the point 1, 1 to the point 2, 4. You can see that here. We're going to rotate that about the y-axis. Okay, so when revolving a function about the y-axis, the surface area can be found by using one of two formulas. One formula is 2 pi integral c to d, the function g of y, times the square root of 1 plus g prime of y squared dy. Or the other formula is surface area can be found by 2 pi integral from a to b, x square root 1 plus f prime of x squared dx. Now, you can try using either one of these formulas. Normally what I do is I just go with the flow. So if they're giving me a function in terms of x, which is what you see here, y equals x squared is a function of x, then I might try using this formula first. But you certainly could use the other formula first. It's just that to use this formula, you would have to find the function g of y, which isn't hard to do, okay? So when we have y equals x squared, that's the same thing as saying f of x is equal to x squared. If you solve this for y, you get the square, if you solve it for x, you get the square root of y is equal to x. And that's the same thing as saying g of y is equal to the square root of y, okay? So you can choose to do it with respect to x, or you can choose to do it with respect to y. Now, it could be that both methods work and both methods are relatively simple, or it could be that one of these is significantly easier than the other. And there really is no way to know, so you just have to go through the process and do it. So let's try it with respect to x first. So we'll call this solution A here. We're going to have surface area equals 2 pi integral from A to B. Well, A and B are going to be 1 and 2, because if we're doing it with respect to x, we have to use the x limits. And then we're going to have the variable x, and then the square root of 1 plus f prime of x squared. So we need f prime of x. Well, if f of x is x squared, then f prime of x is simply 2x. So this is just going to be 2x quantity squared dx. Simplifying just a little bit here, we have the integral x square root 1 plus 2x quantity squared is 4x squared dx. And yes, this is a relatively straightforward integral. We can use basic u substitution here. If I let u equal 1 plus 4x squared, du is going to be 8x dx. So what I need to do to make this work is put an 8 in front of our x here and a 1/8 on the outside. In doing that, on the outside, we have pi over 4, integral of the square root of u times du. And then we do need to change our limits. So when x is equal to 1, u is going to be 5. And when x is equal to 2, u is going to be 1 plus 4 times 2 squared, which is 17. Now we have pi over 4. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. And this goes from 5 to 17. This is going to be 2/3 times pi over 4 u to the 3/2. And this is pi over 6 times 17 to the 3/2 minus 5 to the 3/2. And let's keep in mind that when you have 17 to the 3/2, this is just the square root of 17 times 17 times 17, which can be reduced or simplified to 17 radical 17. So we have pi over 6 times 17 radical 17, and then we could do the same thing with 5 to the 3/2, and we'll end up being 5 radical 5. And so here is our answer. Now let's try to do it with respect to y. To do this with respect to y, we're going to have surface area equals 2 pi times the integral from c to d. And then we have g of y times the square root of 1 plus g prime of y squared dy. So we know that g of y is the square root of y. So we need g prime of y. So g prime of y is going to be 1 over 2 square root of y. So this becomes surface area equals 2 pi times the integral from c to d. Now, c and d are the y limits. Okay, so we have to be looking on the y-axis for that. So it's going to be from 1 to 4. G of y is the square root of y. And then we have the square root of 1 plus g prime of y squared dy. So now we have to simplify this. Well, 1 plus 1 over 2 square root of y quantity squared is 1 plus 1 over 4y, which is 4y over 4y plus 1 over 4y, which can be simplified to 4y plus 1 over 4y. So that is what goes inside the radical here. So what I have is 2 pi integral from 1 to 4, the square root of y times the square root of 4y plus 1 over 4y dy. Now, we can take the square root of the top and the bottom of that fraction, and that will give us the square root of 4y plus 1 divided by, and then when you take the square root of 4y, you're going to get 2 radical y. And what makes this really nice is that the radical y cancels out. Also, the 2 can be factored outside here and put in the denominator, and that's going to make the outside number just pi, and then integral from 1 to 4, square root of 4y plus 1 dy. And from here, we can just use a u substitution. So I'll let u equal 4y plus 1. Du will be 4 times dy. So we'll go ahead and put a 4 in front of our dy here, and a 1/4 on the outside. And this becomes pi over 4 integral of the square root of u times du. And then when y equals 1, u is going to be 5, and when y equals 4, u is going to be 17. Sounds familiar, right? And so we get pi over 4 times the integral of the square root of u is u to the 3/2 divided by 3/2 from 5 to 17. And you might recognize at this point that this is exactly what we ended up with when we did it with respect to x. All right, so when you plug all this stuff in, you are going to get pi over 6, and then when you plug in 17, you will get 17 radical 17, and then when you plug in 5, you'll get 5 radical 5. And so notice that this is the same answer. So I just want to come back to this page and let you know that in my experience, what confuses students the most is having multiple options for the 2 types of problems. The 2 types of problems being when you are rotating around the x-axis or when you are rotating about the y-axis. So the challenge is, of course, you have to memorize these formulas, but then you also have to not get them confused with each other because they are very similar. So this just requires a little bit of studying, and once you get used to it, hopefully it'll get easier for you. And that concludes this video lesson.